Good evening, everyone. My name is Katrina Hernandez, and I'll be presenting to you tonight my vertiport terminal design with dynamic building design for climate and comfort. Throughout history, humans have always sought comfort in their surroundings, whether it's related to temperature, visual appeal, or sound. This quest for comfort has led to the development of passive design strategies. But with advancing technology, we're now witnessing new ways to enhance comfort in our built environments, especially in dynamic architecture. In this study, our main goal is to explore sustainable strategies for designing a vertiport terminal. A vertiport terminal is a specialized infrastructure facility designed for the takeoff and landing and servicing of vertical takeoff and landing aircrafts, such as eVTOL vehicles and drones. Vertiports are intended to support urban air mobility and air taxi services, which aim to provide efficient and rapid aerial transportation within and between urban areas. We will be discussing the following topics: location and climatic analysis, the building design, the dynamic facade design, and the IES simulation results, as well as the conclusion. The vertiport terminal in Queens, New York City is strategically oriented towards the south to maximize winter sunlight. It's situated between Rockaway Boulevard and Nassau Expressway near JFK International Airport, which can generate significant noise. Trees are used to reduce noise and to provide privacy for takeoff and landing areas. Prevailing westerly winds between 30 degrees north and 60 degrees north influence the climate, with southwest winds in the summer and northwest winds in the winter. The site is located in a transportation and utility zone within the airport controlled zone, adjacent to a low-rise residential area. This makes it suitable for its designated land use in the area. Climate analysis, temperature range. The summer months in New York are June, July, and August, and display high warm temperatures that often peak exceeding 30 degrees Celsius. Meanwhile, winter months in New York are from December to February, which shows a wide range of temperatures with significant lows below 0 degrees Celsius. The shaded area indicates the ASHRAE standard comfort zone at 50% relative humidity, which is typically between 20 degrees Celsius and 25 degrees Celsius. Illumination range. In the summer months, there is a notable increase in direct normal illumination, indicating strong direct sunlight during these months, which is expected due to the higher position of the sun in the sky. Both direct normal and global horizontal illumination are at their lowest during the winter, which is consistent with the shorter days and lower position of the sun. Sun shading chart. From December 21 to June 21, the building experiences colder temperatures and requires solar gain for warmth and comfort. Sunshades are generally unnecessary during these months, as unobstructed exposure to the sun is beneficial for about 90% of the time. From June 21 to December 21, when comfort levels are higher, the building can benefit from shading devices. Building design. We start on the right. There are two bubble diagrams that help shape the site in the building. For the bubble diagram of the site layout positions the terminal to maximize southern exposure for enhanced heat and daylight. Landscaping on the north and south provides privacy and noise reduction from nearby traffic. For the building bubble diagram, the terminal's diagram shows departures and arrivals split for smooth drop-offs. Technical and back-of-house areas are on the less occupied east and west sides, with solid walls parallel to the roads for sound insulation. The building's massing concept aims for a sleek and modern geometric structure with dual purposes: an extended facade along the south and the north, and a design reminiscent of flight and departure. Careful angles prevent glare and ensure natural light. The southern glass frontage ensures a clear view of the landing pads, while the passenger drop-off facade along the landside opts for a minimalist approach with vertical glazing for abundant natural light. Some of the sustainable strategies we incorporated for the design is high-performance envelope, solar panels, angled roof and slope glazing, kinetic facade, and some trees and landscape for noise reduction and privacy. The concept of pupils dilating, adapting to changing light conditions is a fascinating inspiration for kinetic architecture design. Just as our eyes respond to their environment, buildings can dynamically adjust to optimize energy efficiency and occupant comfort. This idea resonates with camera lenses, which mimic this natural process to capture the perfect shot. Embracing this concept in architecture not only enhances sustainability, but also echoes the ingenious mechanisms of our eyes and modern photography technology. Since the project is in the United States, I used the LEED rating system. For LEED, the minimum performance requirements is a 5% improvement from the ASHRAE 90.1 standards. However, I want to aim to optimize the performance with a 24% improved efficiency, which will allow the project 10 more points in LEED rating system. Hence, the baseline U values from NYC buildings were improved by 25% for the efficient case. For the IES simulation, the following slides will show some results from some categories for the IES simulation. The simulation would consider the base case, which is application of the minimum requirements, the efficient case, which is application of the green rating system, and the kinetic case, which is application of the kinetic facade. Each case is put under simulation for the winter season, summer season, and autumn season. For the winter season, the coldest day at January 2nd, the summer season, the warmest day at June 14th, and the autumn season, which is the mean temperature at October 8th. All these days and each day will have a simulation at 9 a.m., 12 a.m., and 3 p.m. I've conducted a detailed solar analysis for every season and various times throughout the day. The analysis confirms the building's design effectively harnesses sunlight through its southern facade during the height of winter. In summer, the peak heat is mitigated by sloped glazing, which shades the southern facade, minimizing glare for occupants. During autumn, the building enjoys morning sunlight while the afternoons remain comfortably shaded. For energy consumption analyses, I've compared the base case in blue and the efficient case in red. The chart shows the impact of the optimized envelope performance. In addition, the bar chart shows a significant impact on the energy consumption reduction during the winter months. Ultimately, a 25% optimization on the performance of the envelope allowed the terminal to have a 30% reduction in an annual energy consumption from an annual total of 313 megawatt-hour to 261 megawatt-hour. For the day-night analyses, I've compared the base case with the kinetic case in all three seasons. For all seasons, I have arrived in the same conclusion on how the dynamic facade has helped improve the daylight factor values. For the summer season, the base case shows how the space is overly illuminated. Meanwhile, for the kinetic case, allowed the space to significantly improve. Daylight factor of 14.6 from the base case to 7.8 to the kinetic case. For winter season, we came up with the similar results. Daylight factor of 14.4 from the base case to 7.7 to the kinetic case. Lastly, for autumn season, we came up with the similar results again. Daylight factor of 14.4 from the base case to 8.0 to the kinetic case. The summary of the energy consumption of all cases: the base case at 313 megawatt-hour, the efficient case with a 30% reduction from the base case, while the kinetic case aided in an additional of 10% reduction, totaling to 188 megawatt-hour of annual energy consumption from the original 313 megawatt-hour from the base case. In conclusion, to further enhance the project's sustainability, integrating renewable energy through the addition of approximately 303 photovoltaic panels, each with a 300-watt output, combined with 5 hours of solar exposure per day, could possibly supply 75% of the energy required to operate the facility. Thank you very much.